Learning objectives. In this chapter, the user would learn the following in detail: processes, process concept, process scheduling and operation in processes, cooperating processes, inter-process communication, symmetric versus asymmetric multiprocessing, background process, CPU scheduling, process synchronization, deadlocks. Algorithm evaluation. There are many scheduling algorithms, each with its own parameters. As a result, selecting an algorithm can be difficult. Criteria are often defined in terms of CPU utilization, response time, or throughput. Our criteria may include several measures such as these: maximizing CPU utilization under the constraint that the maximum response time is 1 second, maximizing throughput such that turnaround time is, on average, linearly proportional to total execution time. Once the selection criteria have been defined, we want to evaluate the algorithms under consideration. We describe the various evaluation methods as follows. Deterministic modeling. One major class of evaluation methods is analytic evaluation. Analytic evaluation uses the given algorithm and the system workload to produce a formula or number to evaluate the performance of the algorithm for that workload. Deterministic modeling is one type of analytic evaluation. This method takes a particular predetermined workload and defines the performance of each algorithm for that workload. For example, assume that we have the workload shown below. All 5 processes arrive at time 0 in the order given with the length of the CPU burst given in milliseconds. Process P1, burst time 10. Process P2, burst time 29. Process P3, burst time 3. Process P4, burst time 7. Process P5, burst time 12. Consider the FCFS, SJF, and RR, quantum equaling to 10 milliseconds, scheduling algorithms for this set of processes. Which algorithm would give the minimum average waiting time? For the FCFS algorithm, we would execute the processes as: the waiting time is 0 milliseconds for process P1, 10 milliseconds for process P2, 39 milliseconds for process P3, 42 milliseconds for process P4, and 49 milliseconds for process P5. Thus, the average waiting time is 0 plus 10 plus 39 plus 42 plus 49 divided by 5 equaling 2080 milliseconds. With the RR algorithm, we execute the process as: the waiting time is 10 milliseconds for process P1, 32 milliseconds for process P2, 0 milliseconds for process P3, 3 milliseconds for process P4, and 20 milliseconds for process P5. Thus, the average waiting time is 10 plus 32 plus 0 plus 3 plus 20 divided by 5 equaling 13 milliseconds. With the RR algorithm, we execute the process as: the waiting time is 0 milliseconds for process P1, 32 milliseconds for process P2, 20 milliseconds for process P3, 23 milliseconds for process P4, and 40 milliseconds for process P5. Thus, the average waiting time is 0 plus 32 plus 20 plus 23 plus 40 divided by 5 equaling 23 milliseconds. We can see that in this case the average waiting time obtained with the SJF policy is less than half that obtained with FCFS scheduling. The RR algorithm gives us an intermediate value. Deterministic modeling is simple and fast. It gives us exact numbers, allowing us to compare the algorithms. However, it requires exact numbers for input and its answers apply only to those cases. In cases where we are running the same program over and over again and can measure the program's processing requirements exactly, we may be able to use deterministic modeling to select a scheduling algorithm. Furthermore, over a set of examples, deterministic modeling may indicate trends that can then be analyzed and proved separately. For example, it can be shown that for the environment described, all processes and their times available at time 0, the SGF policy will always result in the minimum waiting time. Queuing models. On many systems, the processes that are run vary from day to day, so there is no static set of processes or times to use for deterministic modeling. What can be determined, however, is the distribution of CPU and input-output bursts. These distributions can be measured and then approximated or simply estimated. The result is a mathematical formula describing the probability of a particular CPU burst. Commonly, this distribution is exponential and is described by its mean. Similarly, we can describe the distribution of times when processes arrive in the system, the arrival time distribution. From these two distributions, it is possible to compute the average throughput, utilization, waiting time, and so on for most algorithms. The computer system is described as a network of servers. Each server has a queue of waiting processes. The CPU is a server with its ready queue, as is the input-output system with its device queues. Knowing arrival rates and service rates, we can compute utilization, average queue length, average wait time, and so on. This area of study is called queuing network analysis. As an example, let n be the average queue length, excluding the process being serviced. Let w be the average waiting time in the queue, and let b the average arrival rate for new processes in the queue, such as 3 processes per second. We expect that during the time w that a process waits, lambda times w new processes will arrive in the queue. If the system is in a steady state, then the number of processes leaving the queue must be equal to the number of processes that arrive. Thus, n equals to lambda times w. This equation, known as Little's formula, is particularly useful because it is valid for any scheduling algorithm and arrival distribution. We can use Little's formula to compute one of these 3 variables if we know the other 2. For example, if we know that 7 processes arrive every second on average, and that there are normally 14 processes in the queue, then we can compute the average waiting time per process as 2 seconds. Queuing analysis can be useful in comparing scheduling algorithms, but it also has limitations. At the moment, the classes of algorithms and distributions that can be handled are fairly limited. The mathematics of complicated algorithms and distributions can be difficult to work with. Thus, arrival and service distributions are often defined in mathematically tractable but unrealistic ways. It is also generally necessary to make a number of independent assumptions which may not be accurate. As a result of these difficulties, queuing models are often only approximations of real-time systems, and the accuracy of computed results may be questionable. Simulations. To get a more accurate evaluation of scheduling algorithms, we can use simulations. Running simulations involves programming a model of the computer system. Software data structures represent the major components of the system. The simulator has a variable representing a clock. As this variable's value is increased, the simulator modifies the system state to reflect the activities of the devices, the processes, and the scheduler. As the simulation executes, statistics that indicate algorithm performance are gathered and printed. The data to drive the simulation can be generated in several ways. The most common method uses a random number generator that is programmed to generate processes, CPU burst times, arrivals, departures, and so on according to probability distributions. The distributions can be defined mathematically, uniform, exponential, Poisson, or empirically. If a distribution is to be defined empirically, measurements of the actual system under study are taken. The results define the distribution of events in the real system. This distribution can then be used to drive the simulation. A distribution-driven simulation may be inaccurate, however, because of relationships between successive events in the real system. The frequency distribution indicates only how many instances of each event occur. It does not indicate anything about the order of their occurrence. To correct this problem, we can use trace tapes. We create a trace tape by monitoring the real system and recording the sequence of actual events. We then use this sequence to drive the simulation. Trace tapes provide an excellent way to compare two algorithms on exactly the same set of real inputs. This method can produce accurate results for its inputs. Simulations can be expensive, often requiring hours of computer time. A more detailed simulation provides more accurate results, but it also takes more computer time. In addition, trace tapes can require large amounts of storage space. Finally, the design, coding, and debugging of the simulator can be a major task. Implementation. Even a simulation is of limited accuracy. The only completely accurate way to evaluate a scheduling algorithm is to code it up, put it in the operating system, and see how it works. This approach puts the actual algorithm in the real system for evaluation under real operating conditions. The major difficulty with this approach is the high cost. The expense is incurred not only in coding the algorithm and modifying the operating system to support it, along with its required data structures, but also in the reaction of the users to a constantly changing operating system. Most users are not interested in building a better operating system. They merely want to get their processes executed and use their results. A constantly changing operating system does not help the users to get their work done. Another difficulty is that the environment in which the algorithm is used will change. The environment will change not only in the usual way as new programs are written and the types of problems change, but also as a result of the performance of the scheduler. If short processes are given priority, then users may break larger processes into sets of smaller processes. If interactive processes are given priority over non-interactive processes, then users may switch to interactive use. For example, researchers designed one system that classified interactive and non-interactive processes automatically by looking at the amount of terminal input-output. If a process did not input or output to the terminal in a 1-second interval, the process was classified as non-interactive and was moved to a lower priority queue. In response to this policy, one programmer modified his programs to write an arbitrary character to the terminal at regular intervals of less than 1 second. The system gave his programs a high priority even though the terminal output was completely meaningless. The most flexible scheduling algorithms are those that can be altered by the system managers or by the users so that they can be tuned for a specific application or set of applications. A workstation that performs high-end graphical applications, for instance, may have scheduling needs different from those of a web server or file server. Some operating systems, particularly several versions of Unix, allow the system manager to fine-tune the scheduling parameters for a particular system configuration. For example, Solaris provides the disadmin command to allow the system administrator to modify the parameters of the scheduling classes. Another approach is to use APIs that can modify the priority of a process or thread. The Java, POSIX, and Windows API provide such functions. The downfall of this approach is that performance tuning a system or application most often does not result in improved performance in more general situations. Background process. It is important to note that while our multiprocessor systems are multiprocessor systems, not all multiprocessor systems are multicore. In our coverage of the multiprocessor systems throughout this text, unless we state otherwise, we generally use the more contemporary term multicore, which excludes some multiprocessor systems. We show a dual-core design with two cores on the same chip. In this design, each core has its own register set as well as its own local cache. Other designs might use a shared cache or a combination of local and shared caches. Aside from architectural considerations such as cache, memory, and bus contention, these multicore CPUs appear to the operating system as N-standard processors. Finally, blade servers are a relatively recent development in which multiple processor boards, input-output boards, and networking boards are placed in the same chassis. The difference between these and traditional multiprocessor systems is that each blade processor board boots independently and runs its own operating system. Some blade server boards are multiprocessor as well, which blurs the lines between types of computers. In essence, these servers consist multiple independent multiprocessor systems. Common division is made between foreground, interactive processes and background, batch processes. These two types of processes have different response time requirements and so may have different scheduling needs. In addition, foreground processes may have priority, externally defined, over background processes. CPU scheduling. CPU scheduling is the basis of multi-programmed operating systems. By switching the CPU among processes, the operating system can make the computer more productive. We also consider the problem of selecting an algorithm for a particular system. On operating systems that support them, it is kernel-level threads, not processes, that are in fact being scheduled by the operating system. However, the terms process scheduling and thread scheduling are often used interchangeably. Basic concepts. In a single processor system, only one process can run at a time. Others must wait until the CPU is freed and can be rescheduled. The objective of multiprogramming is to have some process running at all times to maximize CPU utilization. A process is executed until it must wait, typically for the completion of some input-output request. In a simple computer system, the CPU then just sits idle. All this waiting time is wasted, no useful work is accomplished. With multiprogramming, we try to use this time productively. Several processes are kept in memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues. Every time one process has to wait, another process can take over use of the CPU. Scheduling of this kind is a fundamental operating system function. Almost all computer resources are scheduled before use. The CPU is, of course, one of the primary computer resources. Thus, its scheduling is central to operating system design. CPU Input-Output Burst Cycle. A. Alternating sequence of CPU and input-output burst. B. Histogram of CPU burst durations. The success of CPU scheduling depends on an observed property of processes. Process execution consists of a cycle of CPU execution and input-output wait. Processes alternate between these two states. Process execution begins with a CPU burst. that is followed by an input-output burst, which is followed by another CPU burst, then another input-output burst, and so on. Eventually, the final CPU burst ends with a system request to terminate execution. The durations of CPU bursts have been measured extensively. Although they vary greatly from process to process and from computer to computer, they tend to have a frequency curve similar to that shown below. The curve is generally characterized as exponential or hyperexponential, with a large number of short CPU bursts and a small number of long CPU bursts. An input-output bound program typically has many short CPU bursts. A CPU-bound program might have a few long CPU bursts. This distribution can be important in the selection of an appropriate CPU scheduling algorithm. CPU scheduler. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The selection process is carried out by the short-term scheduler or CPU scheduler. The scheduler selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. Note that the ready queue is not necessarily a first-in, first-out queue. As we shall see when we consider the various scheduling algorithms, a ready queue can be implemented as a first-in, first-out queue, a priority queue, a tree, or simply an unordered linked list. Conceptually, however, all the processes in the ready queue are lined up waiting for a chance to run on the CPU. The records in the queues are generally process control blocks (PCBs) of the processes. Preemptive scheduling. CPU scheduling decisions may take place under the following 4 circumstances. 1. When a process switches from the running state to the waiting state, for example, as the result of an input-output request or an invocation of wait function for the termination of a child process. 2. When a process switches from the running state to the ready state, for example, when an interrupt occurs. 3. When a process switches from the waiting state to the ready state, for example, at completion of input-output. 4. When a process terminates. For situations 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. There is a choice, however, for situations 2 and 3. When scheduling takes place only under circumstances 1 and 4, we say that the scheduling scheme is non-preemptive or cooperative. Otherwise, it is preemptive. Under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the waiting state. This scheduling method was used by Microsoft Windows 3.x. Windows 95 introduced preemptive scheduling, and all subsequent versions of Windows operating systems have used preemptive scheduling. The Mac OS X operating system for the Macintosh also uses preemptive scheduling. Previous versions of the Macintosh operating system relied on cooperative scheduling. Cooperative scheduling is the only method that can be used on certain hardware platforms because it does not require the special hardware, for example, a timer, needed for preemptive scheduling. Unfortunately, preemptive scheduling can result in race conditions when data are shared among several processes. Consider the cases of 2 processes that share data. While one process is updating the data, it is preempted so that the second process can run. The second process then tries to read the data which are in an inconsistent state. Preemption also affects the design of the operating system kernel. During the processing of a system call, kernel may be busy with an activity on behalf of a process. Such activities may involve changing important kernel data, for instance, input-output queues. What happens if the process is preempted in the middle of these changes and the kernel or the device driver needs to read or modify the same structure, chaos ensues. Certain operating systems, including most versions of Unix, deal with this problem by waiting either for a system call to complete or for an input-output block to take place before doing a context switch. The scheme ensures that the kernel structure is simple, since the kernel will not preempt a process while the kernel data structures are in an inconsistent state. Unfortunately, this kernel execution model is a poor one for supporting real-time computing where tasks must complete execution within a given time frame. The operating system needs to accept interrupts at almost all times. Otherwise, input might be lost or output overwritten. So that these sections of code are not accessed concurrently by several processes, they disable interrupts at entry and re-enable interrupts at exit. It is important to note that sections of code that disable interrupts do not occur very often and typically contain few instructions. Dispatcher. Another component involved in the CPU scheduling function is the dispatcher. The dispatcher is the module that gives control of the CPU to the process selected by the short-term scheduler. This function involves the following: switching context, switching to user mode, jumping to the proper location in the user program to restart that program. The dispatcher should be as fast as possible since it is invoked during every process switch. The time it takes for the dispatcher to stop one process and start another running is known as the dispatch latency. Classic problems of synchronization. In this section, we present a number of synchronization problems as example of a large class of concurrency control problems: the bounded buffer problem, the readers-writers problem, the dining philosophers problem. These problems are used for testing nearly every newly proposed synchronization scheme. In our solutions to the problems, we use semaphores for synchronization since that is the traditional way to present such solutions. However, actual implementations of these solutions could use mutex locks in place of binary semaphores. The bounded buffer problem. It is commonly used to illustrate the power of synchronization primitives. Here, we present a general structure of this scheme without committing ourselves to any particular implementation. In our problem, the producer and consumer processes share the following data structures: int n. Semaphore mutex equals 1. Semaphore empty equals n. Semaphore full equals 0. We assume that the pool consists of n buffers, each capable of holding one item. The mutex semaphore provides mutual exclusion for accesses to the buffer pool and is initialized to the value 1. The empty and full semaphores count the number of empty and full buffers. The semaphore empty is initialized to the value n. The semaphore full is initialized to the value 0. The code for the producer process is shown below. The structure of the producer process. The code for the consumer process is shown below. The structure of the consumer process. The readers-writers problem. Suppose that a database is to be shared among several concurrent processes. Some of these processes may want only to read the database, whereas others may want to update, that is, to read and write the database. We distinguish between these two types of processes by referring to the former as readers and to the latter as writers. Obviously, if two readers access the shared data simultaneously, no adverse effects will result. However, if a writer and some other process, either a reader or a writer, access the database simultaneously, chaos may ensue. To ensure that these difficulties do not arise, we require that the writers have exclusive access to the shared database while writing the database. This synchronization problem is referred to as the readers-writers problem. Since it was originally stated, It has been used to test nearly every new synchronization primitive. The readers-writers problem has several variations, all involving priorities. The simplest one, referred to as the first readers-writers problem, requires that no reader be kept waiting unless a writer has already obtained permission to use the shared object. In other words, no reader should wait for other readers to finish simply because a writer is waiting. The second readers-writers problem requires that once a writer is ready, that writer perform its write as soon as possible. In other words, if a writer is waiting to access the object, no new readers may start reading. A solution to either problem may result in starvation. In the first case, writers may starve. In the second case, readers may starve. Solution to the first readers-writers problem. In the solution to the first readers-writers problem, the reader processes share the following data structures: semaphore RW mutex equals 1, semaphore mutex equals 1, int read count equals 0. The semaphores mutex and RW mutex are initialized to 1, read count is initialized to 0. The semaphore RW mutex is common to both reader and writer processes. The mutex semaphore is used to ensure mutual exclusion when the variable read count is updated. The read count variable keeps track of how many processes are currently reading the object. The semaphore RW mutex functions as a mutual exclusion semaphore for the writers. It is also used by the first or last reader that enters or exits the critical section. It is not used by readers who enter or exit while other readers are in their critical sections. The code for a writer process is shown below. The structure of a writer process. The code for a reader process is shown below. The structure of a reader process. Note that if a writer is in the critical section and n readers are waiting, then one reader is queued on RW mutex and n-1 readers are queued on mutex. Also observe that when a writer executes signal RW mutex, we may resume the execution of either the waiting readers or a single waiting writer. The selection is made by the scheduler. The writers-readers problem and its solutions have been generalized to provide reader-writer locks on some systems. Acquiring a reader-writer lock requires specifying the mode of the lock, either read or write access. When a process wishes only to read shared data, it requests the reader-writer lock in read mode. A process wishing to modify the shared data must request the lock in write mode. Multiple processes are permitted to concurrently acquire a reader-writer lock in read mode, but only one process may acquire the lock for writing, as exclusive access is required for writers. Reader-writer locks are most useful in the following situations: in applications where it is easy to identify which processes only read shared data and which processes only write shared data; in applications that have more readers than writers. This is because reader-writer locks generally require more overhead to establish than semaphores or mutual exclusion locks. The increased concurrency of allowing multiple readers compensates for the overhead involved in setting up the reader-writer lock. The dining philosophers problem. Consider 5 philosophers who spend their lives thinking and eating. The philosophers share a circular table surrounded by 5 chairs, each belonging to one philosopher. In the center of the table is a bowl of rice, and the table is laid with 5 single chopsticks. Figure below the situation of dining philosophers. When a philosopher thinks, she does not interact with her colleagues. From time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks that are closest to her, the chopstick that are between her and her left and right neighbors. A philosopher may pick up only 1 chopstick at a time. Obviously, she cannot pick up a chopstick that is already in the hand of a neighbor. When a hungry philosopher has both her chopsticks at the same time, she eats without releasing the chopsticks. When she is finished eating, she puts down both chopsticks and starts thinking again. The dining philosopher's problem is considered a classic synchronization problem, neither because of its practical importance nor because computer scientists dislike philosophers, but because it is an example of a large class of concurrency control problems. It is a simple representation of the need to allocate several resources among several processes in a deadlock-free and starvation-free manner. One simple solution is to represent each chopstick with a semaphore. A philosopher tries to grab a chopstick by executing a wait function operation on that semaphore. She releases her chopsticks by executing the signal function operation on the appropriate semaphores. Thus, the shared data are where all the elements of chopstick are initialized to 1. The structure of philosopher I is shown in program below. Although this solution guarantees that no two neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. Suppose that all 5 philosophers become hungry at the same time and each grabs her left chopstick. All the elements of chopstick will now be equal to 0. When each philosopher tries to grab her right chopstick, she will be delayed forever. Several possible remedies to the deadlock problem are replaced by: allow at most 4 philosophers to be sitting simultaneously at the table. Allow a philosopher to pick up her chopsticks only if both chopsticks are available. To do this, she must pick them up in a critical section. Use an asymmetric solution, that is, an odd-numbered philosopher picks up first her left chopstick and then her right chopstick, whereas an even-numbered philosopher picks up her right chopstick and then her left chopstick. Note, however, that any satisfactory solution to the dining philosopher's problem must guard against the possibility that one of the philosophers will starve to death. A deadlock-free solution does not necessarily eliminate the possibility of starvation. Combined approach to deadlock handling. Combine the 3 basic approaches: prevention, avoidance, detection, allowing the use of the optimal approach for each of resources in the system. Partition resources into hierarchical ordered classes. Use most appropriate technique for handling deadlocks within each class. Cooperating processes. Any process that shares data with other processes is a cooperating process. Independent process cannot affect or be affected by the execution of another process. Cooperating process can affect or be affected by the execution of another process. For example, if a new process shows up and is granted some tickets at the very next lottery, it will have a chance of winning in proportion to the number of tickets it holds. In other words, lottery scheduling is highly responsive. Cooperating processes may exchange tickets if they wish. An alternative example: when a client process sends a message to a server process and then blocks, it may give all of its tickets to the server to increase the chance of the server running next. When the server is finished, it returns the ticket so that the client can run again. In fact, the absence of clients, servers need no tickets at all. To illustrate the concept of cooperating processes, let's consider the producer-consumer problem, which is a common paradigm for cooperating processes. A producer process produces information that is consumed by a consumer process. For example, a compiler may produce assembly code which is consumed by an assembler. The assembler, in turn, may produce object modules which are consumed by the loader. The producer-consumer problem also provides a useful metaphor for the client-server paradigm. We generally think of a server as a producer and a client as a consumer. For example, a web server produces, that is, provides HTML files and images which are consumed, that is, read, by the client web browser requesting the resource. One solution to the producer-consumer problem uses shared memory. To allow producer and consumer processes to run concurrently, we must have available a buffer of items that can be filled by the producer and emptied by the consumer. This buffer will reside in a region of memory that is shared by the producer and consumer processes. Advantages of process cooperation. Information sharing such as shared files. Computation speed up. To run a task faster, we must break it into subtasks, each of which will be executing in parallel. This speed up can be achieved only if the computer has multiple processing elements such as CPUs or input-output channels. Modularity and convenience. Construct a system in a modular function, that is, dividing the system functions into separate processes. One user may have many tasks to work on at one time. For example, a user may be editing, printing, and compiling in parallel. Thread. A thread is a basic unit of CPU utilization. It comprises a thread ID, a program counter, a register set, and a stack. It shares with other threads belonging to the same process its code section, data section, and other operating system resources such as open files and signals. A traditional or heavyweight process has a single thread of control. If a process has multiple threads of control, it can perform more than one task at a time. Figure illustrates the difference between a traditional single-threaded process and a multi-threaded process. Single-threaded and multi-threaded processes. Most software applications that run on modern computers are multi-threaded. An application typically is implemented as a separate process with several threads of control. A web browser might have one thread display images or text, while another thread retrieves data from the network, for example. A word processor may have a thread for displaying graphics, another thread for responding to keystrokes from the user, and a third thread for performing spelling and grammar checking in the background. Applications can also be designed to leverage processing capabilities on multi-core systems. Such applications can perform several CPU-intensive tasks in parallel across the multiple computing cores. Multi-threaded server architecture. In certain situations, a single application may be required to perform several similar tasks. For example, a web server accepts clients' requests for web pages, images, sound, and so forth. A busy web server may have several, perhaps thousands of clients concurrently accessing it. If the web server ran as a traditional single-threaded process, it would be able to service only one client at a time, and a client might have to wait a very long time for its request to be serviced. One solution is to have the server run as a single process that accepts requests. When the server receives a request, it creates a separate process to service that request. In fact, this process creation method was in common use before threads became popular. Process creation is time-consuming and resource-intensive. It is generally more efficient to use one process that contains multiple threads. If the web server process is multi-threaded, the server will create a separate thread that listens for client requests. When a request is made, rather than creating another process, the server creates a new thread to service the request and resume listening for additional requests. This is illustrated in figure below. Threads also play a vital role in remote procedure call RPC systems. Typically, RPC servers are multi-threaded. When a server receives a message, it services the message using a separate thread. This allows the server to service several concurrent requests. Finally, most operating system kernels are now multi-threaded. Several threads operate in the kernel, and each thread performs a specific task such as managing devices, managing memory, or interrupt handling. For example, Solaris has a set of threads in the kernel specifically for interrupt handling. Linux uses a kernel thread for managing the amount of free memory in the system. Benefits. The benefits of multi-threaded programming can be broken down into 4 major categories. First, responsiveness. Multi-threading an interactive application may allow a program to continue running even if part of it is blocked or is performing a lengthy operation, thereby increasing responsiveness to the user. This quality is especially useful in designing user interfaces. For instance, consider what happens when a user clicks a button that results in the performance of a time-consuming operation. A single-threaded application would be unresponsive to the user until the operation had completed. In contrast, if the time-consuming operation is performed in a separate thread, the application remains responsive to the user. Number 2. Resource sharing. Processes can only share resources through techniques such as shared memory and message passing. Such techniques must be explicitly arranged by the programmer. However, threads share the memory and the resources of the process to which they belong by default. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. Economy. Allocating memory and resources for process creation is costly because threads share the resources of the process to which they belong. It is more economical to create and context-switch threads. Empirically, gauging the difference in overhead can be difficult, but in general it is significantly more time-consuming to create and manage processes than threads. In Solaris, for example, creating a process is about 30 times slower than is creating a thread, and context switching is about 5 times slower. Scalability. The benefits of multi-threading can be even greater in a multiprocessing architecture where threads may be running in parallel on different processing cores. A single-threaded process can run on only one processor regardless how many are available. Multi-threading models. Threads may be provided either at the user level for user threads or by the kernel for kernel threads. User threads are supported above the kernel and are managed without kernel support, whereas kernel threads are supported and managed directly by the operating system. Virtually all contemporary operating systems including Windows, Linux, Mac OS X, and Solaris support kernel threads. Ultimately, a relationship must exist between user threads and kernel threads. We look at 3 common ways of establishing such a relationship. The many-to-one model, the one-to-one model, the many-to-many model. The many-to-one model maps many user-level threads to one kernel thread. Thread management is done by the thread library in user space, so it is efficient. However, the entire process will block if a thread makes a blocking system call. Also, because only one thread can access the kernel at a time, multiple threads are unable to run in parallel on multi-core systems. Green threads. A thread library available for Solaris systems and adopted in early versions of Java use the many-to-one model. However, very few systems continue to use the model because of its inability to take advantage of multiple processing cores. One-to-one model. The one-to-one model maps each user thread to a kernel thread. It provides more concurrency than the many-to-one model by allowing another thread to run when a thread makes a blocking system call. It also allows multiple threads to run in parallel on multiprocessors. The only drawback to this model is that creating a user thread requires creating the corresponding kernel thread because the overhead of creating kernel threads can burden the performance of an application. Most implementations of this model restrict the number of threads supported by the system. Linux, along with the family of Windows operating systems, implement the one-to-one model. Many-to-many model. The many-to-many model multiplexes many user-level threads to a smaller or equal number of kernel threads. The number of kernel threads may be specific to either a particular application or a particular machine. An application may be allocated more kernel threads on a multiprocessor than on a single processor. Let's consider the effect of this design on concurrency. Whereas the many-to-one model allows the developer to create as many user threads as she wishes, it does not result in true concurrency because the kernel can schedule only one thread at a time. The one-to-one model allows greater concurrency, but the developer has to be careful not to create too many threads within an application and in some instances may be limited in the number of threads she can create. The many-to-many model suffers from neither of these shortcomings. Developers can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on a multiprocessor. Also, when a thread performs a blocking system call, the kernel can schedule another thread for execution. One variation on the many-to-many model still multiplexes many user-level threads to a smaller or equal number of kernel threads, but also allows a user-level thread to be bound to a kernel thread. This variation is sometimes referred to as the two-level model. The Solaris operating system supported the two-level model in versions older than Solaris 9. However, beginning with Solaris 9, the system uses the one-to-one model. Critical regions. Better higher-level synchronization primitives. Critical regions. Conditional critical regions. Monitors. These were supported in concurrent programming languages. Today's semaphore system calls allow monitor-type synchronization as well. Critical regions. A critical region is a section of code that is always executed under mutual exclusion. Critical regions shift the responsibility for enforcing mutual exclusion from the programmer, where it resides when semaphores are used, to the compiler. They consist of two parts: variables that must be accessed under mutual exclusion, a new language statement that identifies a critical region in which the variables are accessed. All critical regions that are tagged with the same variable have compiler-enforced mutual exclusion so that only one of them can be executed at a time. The processes process A and process B follows. Here, process A can be executing inside its V2 region while process B is executing inside its V1 region, but if they both want to execute inside their respective V1 regions only, one will be permitted to proceed. Each shared variable, V1 and V2 above, has a queue associated with it. Once one process is executing code inside a region tagged with a shared variable, any other processes that attempt to enter a region tagged with the same variable are blocked and put in the queue. Producer-consumer code with CRs. Conditional critical regions provide conditions synchronization for critical regions. Where B is a Boolean expression, usually B will refer to V, conditional critical regions work as follows. A process wanting to enter a region for V must obtain the mutex lock. If it cannot, then it is queued. Once the lock is obtained, the Boolean expression B is tested. If B evaluates to true, then the process proceeds. Otherwise, it releases the lock and is queued. When it next gets the lock, it must retest B. Producer-consumer code with CCRs. Deadlock Avoidance. Deadlock prevention algorithms prevent deadlocks by limiting how requests can be made. The limits ensure that at least one of the necessary conditions for deadlock cannot occur. Possible side effects of preventing deadlocks by this method, however, are low device utilization and reduced system throughput. An alternative method for avoiding deadlocks is to require additional information about how resources are to be requested. For example, in a system with one tape drive and one printer, the system might need to know that process P will request first the tape drive and then the printer before releasing both resources, whereas process Q will request first the printer and then the tape drive. With this knowledge of the complete sequence of requests and releases for each process, the system can decide for each request whether or not the process should wait in order to avoid a possible future deadlock. Each request requires that in making this decision, the system consider the resources currently available, the resources currently allocated to each process, and the future requests and releases of each process. The various algorithms that use this approach differ in the amount and type of information required. The simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. Given this priority information, it is possible to construct an algorithm that ensures that the system will never enter a deadlocked state. A deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that a circular wait condition can never exist. The resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. In the following sections, we explore two deadlock avoidance algorithms. Safe state. A state is safe if the system can allocate resources to each process up to its maximum in some order and still avoid a deadlock. More formally, a system is in a safe state only if there exists a safe sequence. A sequence of processes P1, P2, and so on till Pn is a safe sequence for the current allocation state if, for each Pi, the resource requests that Pi can still make can be satisfied by the currently available resources plus the resources held by all Pj with j less than I. In this situation, if the resources that Pi needs are not immediately available, then Pi can wait until all Pj has finished. When they have finished, Pi can obtain all of its needed resources, complete its designated task, return its allocated resources, and terminate. When Pi terminates, Pi plus 1 can obtain its needed resources, and so on. If no such sequence exists, then the system state is said to be unsafe. A safe state is not a deadlocked state. Conversely, a deadlocked state is an unsafe state. Not all unsafe states are deadlocks. Figure shows safe, unsafe state, and deadlock state. An unsafe state may lead to a deadlock. As long as the state is safe, the operating system can avoid unsafe and deadlocked states. In an unsafe state, the operating system cannot prevent processes from requesting resources in such a way that a deadlock occurs. The behavior of the processes controls unsafe states. To illustrate, we consider a system with 12 magnetic tape drives and 3 processes, P0, P1, and P2. Process P0 requires 10 tape drives, process P1 may need as many as 4 tape drives, and process P2 may need up to 9 tape drives. Suppose that at time T0, process P0 is holding 5 tape drives, process P1 is holding 2 tape drives, and process P2 is holding 2 tape drives. Thus, there are 3 free tape drives. Refer to table below. At the time T0, the system is in a safe state. The sequence P1, P0, P2 satisfies the safety condition. Process P1 can immediately be allocated all its tape drives and then return them. The system will then have 5 available tape drives. Then process P0 can get all its tape drives and return them. The system will then have 10 available tape drives. And finally, process P2 can get all its tape drives and return them. The system will then have all 12 tape drives available. A system can go from a safe state to an unsafe state. Suppose that at time t1, process P2 requests and is allocated one more tape drive. The system is no longer in a safe state. At this point, only processes P1 can be allocated all its tape drives. When it returns them, the system will have only 4 available tape drives. Since process P0 is allocated 5 tape drives but has a maximum of 10, it may request 5 more tape drives. If it does so, it will have to wait because they are unavailable. Similarly, process P2 may request 6 additional tape drives and have to wait, resulting in a deadlock. Our mistake was in granting the request from process P2 for one more tape drive. If we had made P2 wait until either of the other processes had finished and released its resources, then we could have avoided the deadlock. Given the concept of a safe state, we can define avoidance algorithms that ensure that the system will never deadlock. The idea is simply to ensure that the system will always remain in a safe state. Initially, the system is in a safe state. Whenever a process requests a resource that is currently available, the system must decide whether the resource can be allocated immediately or whether the process must wait. The request is granted only if the allocation leaves the system in a safe state. In this scheme, if a process requests a resource that is currently available, it may still have to wait. Thus, resource utilization may be lower than it would otherwise be. Resource Allocation Graph Algorithm. If we have a resource allocation system with only one instance of each resource type, we can use a variant of the resource allocation graph defined for deadlock avoidance. In addition to the request and assignment edges, we introduce a new type of edge called a claim edge. A claim edge, Pi leads to Rj, indicates that process Pi may request resource Rj at some time in the future. The edge resembles a request edge in direction, but it is represented in the graph by a dashed line. When process Pi requests resource Rj, the claim edge Pi leads to Rj is converted to a request edge. Similarly, when a resource Rj is released by Pi, the assignment edge Rj leads to Pi is reconverted to a claim edge Pi leads to Rj. Note that the resources must be claimed a priori in the system. That is, before process Pi starts executing, all its claim edges must already appear in the resource allocation graph. We can relax this condition by allowing a claim edge Pi leads to Rj to be added to the graph only if all the edges associated with the process Pi are claim edges. To illustrate this algorithm, we consider the resource allocation graph of figure below. Resource allocation graph for the deadlock avoidance. Suppose that P2 requests R2. Although R2 is currently free, we cannot allocate it to P2 since this action will create a cycle in the graph. Figure an unsafe state in a resource allocation graph. Banker's algorithm. Safety algorithm. Resource request algorithm. Resource allocation graph algorithm is not applicable to a resource allocation system with multiple instances of each resource type. The deadlock avoidance algorithm that we describe next is applicable to such a system but is less efficient than the resource allocation graph scheme. This algorithm is commonly known as the banker's algorithm. The name was chosen because the algorithm could be used in a banking system to ensure that the banker never allocated its available cash in such a way that it could no longer satisfy the needs of all its customers. When a new process enters the system, it must declare the maximum number of instances of each resource type that it may need. This number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state. If it will, the resources are allocated. Otherwise, the process must wait until some other process releases enough resources. Several data structures must be maintained to implement the banker's algorithm. These data structures encode the state of the resource allocation system. We need the following data structures, where n is the number of processes in the system and m is the number of resource types. Available. A vector of length m indicates the number of available resources of each type. If available j equals k, then k instances of resources type rj are available. Max. An n times m matrix defines the maximum demand of each process. If max I and j equals k, then process Pi may request at most k instances of resources type rj. Allocation. An n times m matrix defines the number of resources of each type currently allocated to each process. If allocation of I variable into j variable equals k, then process P1 is currently allocated k instances of resource type rj. Need. An n times m matrix indicates the remaining resource need of each process. If need I of j equals k, then process Pi may need k more instances of resource type rj to complete its task. Note that need I of j equals max I of j minus allocation I of j. These data structures vary over time in both size and value. To simplify the presentation of the banker's algorithm, we next establish some notation. Let x and y be vectors of length n. We say that x is lesser than or equal to y if and only if x variable I is lesser than or equal to y variable I for all y equals to 1, 2, and so forth till n. For example, if x equals to 1, 7, 3, 2, and y equals to 0, 3, 2, 1, then y is lesser than or equal to x. In addition, y lesser than x if y is equal to or lesser than x and y is equal to x. We can treat each row in the matrices allocation and need as vectors and refer to them as allocation I and need I. The vector allocation I specifies the resource currently allocated to process Pi. The vector need I specifies the additional resources that process Pi may still request to complete its task. Safety algorithm. We can now present the algorithm for finding out whether or not a system is in a safe state. This algorithm can be described as follows. 1. Let work and finish be vectors of length m and n respectively. Initialize work equals available and finish I equals false for I equals to 0, 1, and so on till n minus 1. 2. Find an index I such that both a. Finish I is equal to false, b. Quest I is lesser than or equal to work. If no such I exists, go to step 4. Work equals work plus allocation I. Finish I equals to true. Go to step 2. If finish I is equal to true for all I, then the system is in a safe state. This algorithm may require an order of m times n to the power of 2 operations to determine whether a state is safe. Resource and request algorithm. Next, we describe the algorithm for determining whether requests can be safely granted. Let request I be the request vector for processes Pi. If request j is equal to or not equal to k, then process Pi wants k instances of resource type Rj. When a request for resources is made by processes Pi, the following actions are taken. 1. If request I is lesser than or equal to need I, go to step 2. Otherwise, raise an error condition since the process has exceeded its maximum claim. 2. If request I is lesser than or equal to available, go to step 3. Otherwise, Pi must wait since the resources are not available. Have the system pretend to have allocated the requested resources to process Pi by modifying the state as follows. Available equals to available minus request I. Allocation I equals to allocation I plus request I. Need I equals to need I minus request I. If the resulting resource allocation state is safe, the transaction is completed and process Pi is allocated its resources. However, if the new state is unsafe, then Pi must wait for request I and the old resource allocation state is restored. Deadlock characterization. In a deadlock, processes never finish executing and system resources are tied up, preventing other jobs from starting. We discuss the features that characterize deadlocks. Necessary conditions. Resource allocation graph. Necessary conditions. A deadlock situation can arise if the following 4 conditions hold simultaneously in a system. Mutual exclusion. At least one resource must be held in a non-shareable mode, that is, only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. Hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. No preemption. Resources cannot be preempted, that is, a resource can be released only voluntarily by the process holding it after that process has completed its task. Circular wait. A set P0, P1 and so on to Pn of waiting processes must exist such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, and so on. Pn minus 1 is waiting for a resource held by Pn, and Pn is waiting for a resource held by P0. We emphasize that all 4 conditions must hold for a deadlock to occur. The circular wait condition implies the hold and wait condition, so the 4 conditions are not completely independent. However, that it is useful to consider each condition separately. Resource allocation graph. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This graph consists of a set of vertices V and a set of edges E. The set of vertices V is partitioned into 2 different types of nodes, P equals P1, P2 and so on till Pn. The set consisting of all the active processes in the system, and R equals to R1, R2 and so on till Rm. The set consisting of all resource types in the system. A directed edge from process Pi to resource type Rj is denoted by Pi to Rj. It signifies that process Pi has requested an instance of resource type Rj and is currently waiting for that resource. A directed edge from resource type Rj to process Pi is denoted by Rj to Pi. It signifies that an instance of resource type Rj has been allocated to process Pi. A directed edge Pi to Rj is called a request edge. A directed edge Rj to Pi is called an assignment edge. Pictorially, we represent each process Pi as a circle and each resource type Rj as a rectangle. Since resource type Rj may have more than one instance, we represent each such instance as a dot within the rectangle. Note that a request edge points to only the rectangle Rj, whereas an assignment edge must also designate one of the dots in the rectangle. When process Pi requests an instance of resource type Rj, a request edge is inserted in the resource allocation graph. When this request can be fulfilled, the request edge is instantaneously transformed to an assignment edge. When the process no longer needs access to the resource, it releases the resource. As a result, the assignment edge is deleted. The resource allocation graph shown in figure below depicts the following situation. The sets P, R, and E. P equals P1, P2, P3. R equals R1, R2, R3, R4. E equals P1 follows to R1, P2 follows to R3, R1 follows to P2, R2 follows to P2, R2 follows to P1, and R3 follows to P3. Resource instances. One instance of resource type R1, two instances of resource type R2, one instance of resource type R3, three instances of resource type R4. Process states. Process P1 is holding an instance of resource type R2 and is waiting for an instance of resource type R1. Process P2 is holding an instance of R1 and an instance of R2 and is waiting for an instance of R3. Process P3 is holding an instance of R3. Given the definition of a resource allocation graph, it can be shown that if the graph contains no cycles, then no process in the system is deadlocked. If the graph does not contain a cycle, then a deadlock may exist. If each resource type has exactly one instance, then a cycle implies that a deadlock has occurred. If the cycle involves only a set of resource types, each of which has only a single instance, then a deadlock has occurred. Each process involved in the cycle is deadlocked. In this case, a cycle in the graph is both a necessary and a sufficient condition for the existence of deadlock. If each resource type has several instances, then a cycle does not necessarily imply that a deadlock has occurred. In this case, a cycle in the graph is a necessary but not a sufficient condition for the existence of deadlock. Suppose that process P3 requests an instance of resource type R2. Since no resource instance is currently available, we add a request edge P3 leads to R2 to the graph. Resource allocation graph with a deadlock. At this point, two minimal cycles exist in the system. Processes P1, P2, and P3 are deadlocked. Process P2 is waiting for the resource R3, which is held by process P3. Process P3 is waiting for either process P1 or process P2 to release resource R2. In addition, process P1 is waiting for process P2 to release resource R1. Now consider the resource allocation graph in figure below. Resource allocation graph with a cycle but no deadlock. In this example, we also have a cycle. However, there is no deadlock. Observe that process P4 may release its instance of resource type R2. That resource can then be allocated to P3, breaking the cycle. In summary, if a resource allocation graph does not have a cycle, then the system is not in a deadlocked state. If there is a cycle, then the system may or may not be in a deadlocked state. This observation is important when we deal with the deadlock problem. Deadlock detection. If a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur. In this environment, the system may provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, an algorithm to recover from the deadlock. In the following discussion, we elaborate on these two requirements as they pertain to systems with only a single instance of each resource type, as well as to systems with several instances of each resource type. At this point, however, we note that a detection and recovery scheme requires overhead that includes not only the runtime costs of maintaining the necessary information and executing the detection algorithm, but also the potential losses inherent in recovering from a deadlock. Single instance of each resource type, several instances of a resource type, detection algorithm usage. Single instance of each resource type. If all resources have only a single instance, then we can define a deadlock detection algorithm that uses a variant of the resource allocation graph called a wait-for graph. We obtain this graph from the resource allocation graph by removing the resource nodes and collapsing the appropriate edges. More precisely, an edge from Pi to Pj in a wait-for graph implies that process Pi is waiting for process Pj to release a resource that Pi needs. An edge Pi goes to Pj exists in a wait-for graph if and only if the corresponding resource allocation graph contains two edges, Pi goes to Rq and Rq goes to Pj for some resource Rq. In figure below, we present a resource allocation graph and the corresponding wait-for graph. As before, a deadlock exists in the system if and only if the wait-for graph contains a cycle. To detect deadlocks, the system needs to maintain the wait-for graph and periodically invoke an algorithm that searches for a cycle in the graph. An algorithm to detect a cycle in a graph requires an order of n to the power of 2 operations, where n is the number of vertices in the graph. Several instances of a resource type. The wait-for graph scheme is not applicable to a resource allocation system with multiple instances of each resource type. We turn now to a deadlock detection algorithm that is applicable to such a system. The algorithm employs several time-varying data structures that are similar to those used in the banker's algorithm. Available. A vector of length m indicates the number of available resources of each type. Allocation. An n times m matrix defines the number of resources of each type currently allocated to each process. Request. An n times m matrix indicates the current request of each process. If request I into j equals k, then process Pi is requesting k more instances of resource type Rj. To simplify notation, we again treat the rows in the matrices allocation and request as vectors. We refer to them as allocation I and request I. The detection algorithm described here simply investigates every possible allocation sequence for the processes that remain to be completed. Compare this algorithm with the banker's algorithm. Let work and finish be vectors of length m and n respectively. Initialize work equals available for I equals to 0, 1, so on till n minus 1. If allocation I equals to 0, then finish into variable j equals false. Otherwise, finish into variable j equals true. Find an index I such that both finish I is equal to false, request I is lesser than or to work. If no such I exists, go to step 4. Work equals to work plus allocation I. Finish I equals to true. Go to step 2. If finish I is equal to false for some I, 0 is lesser than or equal to I, which is lesser than n, then the system is in a deadlocked state. Moreover, if finish I is equal to false, then process Pi is deadlocked. This algorithm requires an order of m times n to the power of 2 operations to detect whether the system is in a deadlocked state. To illustrate this algorithm, we consider a system with 5 processes P0 through P4 and 3 resource types A, B, and C. Resource type A has 7 instances, resource type B has 2 instances, and resource type C has 6 instances. Suppose that at time t0 we have the following resource allocation state. Allocation request available as follows. We claim that the system is not in a deadlocked state. Indeed, if we execute our algorithm, we will find that the sequence P0, P2, P3, P1, and P4 results in finish I equals to or true for all I. Suppose now that process P2 makes one additional request for an instance of type C. The request matrix is modified as follows. We claim that the system is now deadlocked. Although we can reclaim the resources held by process P0, the number of available resources is not sufficient to fulfill the requests of the other processes. Thus, a deadlock exists consisting of processes P1, P2, P3, and P4. Detection algorithm usage. When should we invoke the detection algorithm? The answer depends on 2 factors. 1. How often is a deadlock likely to occur? 2. How many processes will be affected by deadlock when it happens? If deadlocks occur frequently, then the detection algorithm should be invoked frequently. Resources allocated to deadlocked processes will be idle until the deadlock can be broken. In addition, the number of processes involved in the deadlock cycle may grow. Deadlocks occur only when some processes make a request that cannot be granted immediately. This request may be the final request that completes a chain of waiting processes. In the extreme, then, we can invoke the deadlock detection algorithm every time a request for allocation cannot be granted immediately. In this case, we can identify not only the deadlocked set of processes but also the specific process that caused the deadlock. In reality, each of the deadlocked processes is a link in the cycle of the resource graph, so all of them jointly caused the deadlock. If there are many different resource types, one request may create many cycles in the resource graph, each cycle completed by the most recent request and caused by the one identifiable process. Of course, invoking the deadlock detection algorithm for every resource request will incur considerable overhead in computation time. A less expensive alternative is simply to invoke the algorithm at defined intervals, for example, once per hour or whenever CPU utilization drops below 40%. A deadlock eventually cripples system throughput and causes CPU utilization to drop. If the detection algorithm is invoked at arbitrary points in time, the resource graph may contain many cycles. In this case, we generally cannot tell which of the many deadlocked processes caused the deadlock processes, but also the specific process that caused the deadlock. In reality, each of the deadlocked processes is a link in the cycle in this resource graph, so all of them jointly caused deadlock. If there are many different resource types, one request may create many cycles in the resource graph, each cycle completed by the most recent request and caused by the one identifiable process. Of course, invoking the deadlock detection algorithm for every resource request will incur considerable overhead in computation time. A less expensive alternative is simply to invoke the algorithm at defined intervals. For example, once per hour or whenever CPU utilization drops below 40%. A deadlock eventually cripples system throughput and causes CPU utilization to drop. If the detection algorithm is invoked at arbitrary points in time, the resource graph may contain many cycles. In this case, we generally cannot tell which of the many deadlocked processes caused the deadlock. Deadlock Prevention. For a deadlock to occur, each of the 4 necessary conditions must hold. By ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadlock. We elaborate on this approach by examining each of the 4 necessary conditions separately. Mutual exclusion. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources, in contrast, do not require mutually exclusive access and thus cannot be involved in a deadlock. Read-only files are a good example of a shareable resource. If several processes attempt to open a read-only file at the same time, they can be granted simultaneous access to the file. A process never needs to wait for a shareable resource. In general, however, we cannot prevent deadlocks by denying the mutual exclusion condition because some resources are intrinsically non-shareable. For example, a mutex lock cannot be simultaneously shared by several processes. Hold and wait. To ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resources. One protocol that we can use requires each process to request and be allocated all its resources before it begins execution. We can implement this provision by requiring that system calls requesting resources for a process precede all other system calls. An alternative protocol allows a process to request resources only when it has none. A process may request some resources and use them. Before it can request any additional resources, it must release all the resources that it is currently allocated. To illustrate the difference between these two protocols, we consider a process that copies data from a DVD drive to a file on disk, sorts the file, and then prints the results to a printer. If all resources must be requested at the beginning of the process, then the process must initially request the DVD drive, disk file, and printer. It will hold the printer for its entire execution even though it needs the printer only at the end. The second method allows the process to request initially only the DVD drive and disk file. It copies from the DVD drive to the disk and then releases both the DVD drive and the disk file. The process must then request the disk file and the printer. After copying the disk file to the printer, it releases these two resources and terminates. Both these protocols have two main disadvantages. Resource utilization may be low since resources may be allocated but unused for a long period. In the example given, for instance, we can release the DVD drive and disk file and then request the disk file and printer only if we can be sure that our data will remain on the disk file. Otherwise, we must request all resources at the beginning for both protocols. Starvation is possible. A process that needs several popular resources may have to wait indefinitely because at least one of the resources that it needs is always allocated to some other process. No preemption. The third necessary condition for deadlocks is that there be no preemption of resources that have already been allocated. To ensure that this condition does not hold, we can use the following protocol. If a process is holding some resources and requests another resource that cannot be immediately allocated to it, that is, the process must wait, then all resources the process is currently holding is preempted. In other words, these resources are implicitly released. The preempted resources are added to the list of resources for which the process is waiting. The process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. Alternatively, if a process requests some resources, we first check whether they are available. If they are, we allocate them. If they are not, we check whether they are allocated to some other process that is waiting for additional resources. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. If the resources are neither available nor held by a waiting process, the requesting process must wait. While it is waiting, some of its resources may be preempted, but only if another process requests them. A process can be restarted only when it is allocated the new resources it is requesting and recovers any resources that we preempted while it was waiting. This protocol is often applied to resources whose state can be easily saved and restored later, such as CPU registers and memory space. It cannot generally be applied to such resources as mutex locks and semaphores. Circular wait. The fourth and final condition for deadlocks is the circular wait condition. One way to ensure that this condition never holds is to impose a total ordering of all resource types and to require that each process requests resources in an increasing order of enumeration. To illustrate, we let R equals R1, R2, and so on till Rm be the set of resource types. We assign to each resource type a unique integer number which allows us to compare two resources and to determine whether one precedes another in our ordering. Formally, we define a one-to-one function f, that is, R leads to n, where n is the set of natural numbers. For example, if the set of resource types R includes tape drives, disk drives, and printers, then the function f might be defined as follows. F tape drive equals 1, f disk drive equals 5, f printer equals 12. We can now consider the following protocol to prevent deadlocks. Each process can request resources only in an increasing order of enumeration. That is, a process can initially request any number of instances of a resource type, say Ri. After that, the process can request instances of resource type of Rj if and only if f function Rj is greater than f function Ri. For example, using the function defined previously, a process that wants to use the tape drive and printer at the same time must first request the tape drive and then request the printer. Alternatively, we can require that a process requesting an instance of a resource type Rj must have released any resources Ri such that f function Ri is equal to or greater than f function Rj. Note also that if several instances of the same resource type are needed, a single request for all of them must be issued. If these two protocols are used, then the circular wait condition cannot hold. We can demonstrate this fact by assuming that a circular wait exists, proof by contradiction. Let the set of processes involved in the circular wait be P0, P1, and so on till Pn, where Pi is waiting for a resource Ri which is held by process Pi plus 1. Modular arithmetic is used on the indexes so that Pn is waiting for a resource Rn held by P0. Then, since processes Pi plus 1 is holding resource Ri, while requesting resource Ri plus 1, we must have f Ri function lesser than f Ri plus 1 function for all I, but this condition means that f R0 function is lesser than f R1 function is lesser than as follows is lesser than f Rn function is lesser than f R0 function. By transitivity, f R0 function is lesser than f R0 function, which is impossible. Therefore, there can be no circular wait. We can accomplish this scheme in an application program by developing an ordering among all synchronization objects in the system. All requests for synchronization objects must be made in increasing order. F first mutex function equals to 1, f second mutex function equals to 5. For example, if the lock ordering in the pthread program shown in figure, Deadlock example was then thread 2 could not request the locks out of order. Keep in mind that developing an ordering or hierarchy does not in itself prevent deadlock. It is up to application developers to write programs that following the ordering. Also note that the function f should be defined according to the normal order of usage of the resources in a system. For example, because the tape drive is usually needed before the printer, it would be reasonable to define f tape drive function is lesser than f printer function. Although ensuring that resources are acquired in the proper order is the responsibility of application developers, certain software can be used to verify that locks are acquired in the proper order and to give appropriate warnings when locks are acquired out of order and deadlock is possible. One lock order verifier which works on BSD versions of Unix such as FreeBSD is known as Witness. Witness uses mutual exclusion locks to protect critical sections. It works by dynamically maintaining the relationship of lock orders in a system. Let's use the program shown above as an example. Assume that thread 1 is the first to acquire the locks and does so in the order 1. First mutex, 2. Second mutex. Witness records the relationship that first mutex must be acquired before second mutex. If thread 2 later acquires the locks out of order, Witness generates a warning message on the system console. It is also important to note that imposing a lock ordering does not guarantee deadlock prevention if locks can be acquired dynamically. For example, assume we have a function that transfers funds between two accounts. To prevent a race condition, each account has an associated mutex lock that is obtained from a getLock function such as shown below. Deadlock example with lock ordering. Deadlock is possible if two threads simultaneously invoke the transaction function transposing different accounts. That is, one thread might invoke transaction and another might invoke transaction. We leave it as an exercise for students to fix this situation. Deadlocks. In a multi-programming environment, several processes may compete for a finite number of resources. A process requests resources. If the resources are not available at that time, the process enters a waiting state. Sometimes a waiting process is never again able to change state because the resources it has requested are held by other waiting processes. This situation is called a deadlock. In this chapter, we describe methods that an operating system can use to prevent or deal with deadlocks. Although some applications can identify programs that may deadlock, operating systems typically do not provide deadlock prevention facilities, and it remains the responsibility of programmers to ensure that they design deadlock-free programs. System model. A system consists of a finite number of resources to be distributed among a number of competing processes. The resources may be partitioned into several waiting for an event that can be caused only by another process in the set. The types or classes, each consisting of some number of identical instances. CPU cycles, files, and input-output devices such as printers and DVD drives are examples of resource types. If a system has two CPUs, then the resource type CPU has two instances. Similarly, the resource type printer may have 5 instances. If a process requests an instance of a resource type, the allocation of any instance of the type should satisfy the request. If it does not, then the instances are not identical and the resource type classes have not been defined properly. For example, a system may have 2 printers. These 2 printers may be defined to be in the same resource class if no one cares which printer prints which output. However, if one printer is on the 9th floor and the other is on the basement, then people on the 9th floor may not see both printers as equivalent, and separate resource classes may need to be defined for each printer. Synchronization tools such as mutex locks and semaphores are also considered system resources, and they are a common source of deadlock. However, a lock is typically associated with protecting a specific data structure. That is, one lock may be used to protect access to a queue, another to protect access to a linked list, and so forth. For that reason, each lock is typically assigned to its own resource class, and definition is not a problem. A process must request a resource before using it and must release the resource after using it. A process may request as many resources as it requires to carry out its designated task. Obviously, the number of resources requested may not exceed the total number of resources available in the system. In other words, a process cannot request 3 printers if the system has only 2. Under the normal mode of operation, a process may utilize a resource in only the following sequence. Request. The process requests the resource. If the request cannot be granted immediately, for example, if the resource is being used by another process, then the requesting process must wait until it can acquire the resource. Use. The process can operate on the resource. For example, if the resource is a printer, the process can print on the printer. Release. The process releases the resource. The request and release of resources may be system calls. Examples are the requests function and release function, device, open and close function file, and allocate function and free function memory system calls. Similarly, the request and release of semaphores can be accomplished through the wait function and signal function operations on semaphores or through acquire function and release function of a mutex lock. For each use of a kernel-managed resource by a process or thread, the operating system checks to make sure that the process has requested and has been allocated the resource. A system table records whether each resource is free or allocated. For each resource that is allocated, the table also records the process to which it is allocated. If a process requests a resource that is currently allocated to another process, it can be added to a queue of processes waiting for this resource. A set of processes is in a deadlocked state when every process in the set is waiting for an event that can be caused only by another process in the set. The events with which we are mainly concerned here are resource acquisition and release. The resources may be either physical resources, for example, printers, tape drives, memory space, and CPU cycles, or logical resources, for example, semaphores, mutex locks, and files. However, other types of events may result in deadlocks, for example, the IPC facilities. To illustrate a deadlocked state, consider a system with 3 CD-RW drives. Suppose each of 3 processes holds one of these CD-RW drives. If each process now requests another drive, the 3 processes will be in a deadlock state. Each is waiting for the event CD-RW is released, which can be caused only by one of the other waiting processes. This example illustrates a deadlock involving the same resource type. Deadlocks may also involve different resource types. For example, consider a system with 1 printer and 1 DVD drive. Suppose that process PI is holding the DVD and process PJ is holding the printer. If PI requests the printer and PJ requests the DVD drive, a deadlock occurs. Inter-process communication. Processes executing concurrently in the operating system may be either independent processes or cooperating processes. A process is independent if it cannot affect or be affected by the other processes executing in the system. Any process that does not share data with any other process is independent. A process is cooperating if it can affect or be affected by the other processes executing in the system. Clearly, any process that shares data with the other processes is a cooperating process. There are several reasons for providing an environment that allows process cooperation. Information sharing. Since several users may be interested in the same piece of information, for instance, a shared file, we must provide an environment to allow concurrent access to such information. Computation speed up. If we want a particular task to run faster, we must break it into subtasks, each of which will be executing in parallel with the others. Notice that such a speed-up can be achieved only if the computer has multiple processing cores. Modularity. We may want to construct the system in a modular fashion, dividing the system functions into separate processes or threads. Convenience. Even an individual user may work on many tasks at the same time. For instance, a user may be editing, listening to music, and compiling in parallel. Cooperating processes require an inter-process communication (IPC) mechanism that will allow them to exchange data and information. These are two fundamental models of inter-process communication: shared memory and message passing. In the shared memory model, a region of memory that is shared by cooperating processes is established. Processes can then exchange information by reading and writing data to the shared region. In the message passing model, communication takes place by means of messages exchanged between the cooperating processes. The two communication models: A. Message passing, B. Shared memory. Both of the models just mentioned are common in operating systems, and many systems implement both. Message passing is useful for exchanging smaller amounts of data because no conflicts need be avoided. Message passing is also easier to implement in a distributed system than shared memory. Although there are systems that provide distributed shared memory, we do not consider them in this text. Shared memory can be faster than message passing since message passing systems are typically implemented using system calls memory regions. Once shared memory is established, all accesses are treated as routine memory accesses and no assistance from the kernel is required. Recent research on systems with several processing cores indicates that message passing provides better performance than shared memory on such systems. Shared memory suffers from the cache coherency issues which arise because shared data migrate among the several caches. As the number of processing cores on systems increases, it is possible that we will see message passing as the preferred mechanism for IPC. Shared memory systems. Inter-process communication using shared memory requires communicating processes to establish a region of shared memory. Typically, a shared memory region resides in the address space of the process creating the shared memory segment. Other processes that wish to communicate using this shared memory segment must attach it to the address space. Normally, the operating system tries to prevent one process from accessing another process's memory. Shared memory requires that two or more processes agree to remove this restriction. They can then exchange information by reading and writing data in the shared areas. The form of the data and the location are determined by these processes and are not under the operating system's control. The processes are also responsible for ensuring that they are not writing to the same location simultaneously. To illustrate the concept of cooperating processes, let's consider the producer-consumer problem, which is a common paradigm for cooperating processes. A producer process produces information that is consumed by a consumer process. For example, a compiler may produce assembly code that is consumed by an assembler. The assembler, in turn, may produce object modules that are consumed by the loader. The producer-consumer problem. The producer process using shared memory. The producer-consumer problem also provides a useful metaphor for the client-server paradigm. We generally think of a server as a producer and a client as a consumer. For example, a web server produces, that is, provides, HTML files and images, which are consumed, that is, read by the client web browser requesting the resource. One solution to the producer-consumer problem uses shared memory. To allow the producer and consumer processes to run concurrently, we must have available a buffer of items that can be filled by the producer and emptied by the consumer. This buffer will reside in a region of memory that is shared by the producer and consumer processes. A producer can produce one item while the consumer is consuming another item. The producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. Two types of buffers can be used. The unbounded buffer places no practical limit on the size of the buffer. The consumer may have to wait for new items, but the producer can always produce new items. The bounded buffer assumes a fixed buffer size. In this case, the consumer must wait if the buffer is empty and the producer must wait if the buffer is full. Let's look more closely at how the bounded buffer illustrates inter-process communication using shared memory. The following variables reside in a region of memory shared by the producer and consumer processes. The shared buffer is implemented as a circular array with two logical pointers, in and out. The variable in points to the text-free position in the buffer. Out points to the first full position in the buffer. The buffer is empty when in double equals out. The buffer is full when in plus 1% buffer size double equals out. The consumer process using shared memory. The code for the consumer process is shown below. The producer process has a local variable next produced in which the new item to be produced is stored. The consumer process has a local variable next consumed in which the item to be consumed is stored. This scheme allows at most buffer size 1 items in the buffer at the same time. We leave it as an exercise for you to provide a solution in which buffer size items can be in the buffer at the same time. One issue this illustration does not address concerns the situation in which both the producer process and the consumer process attempt to access the shared buffer concurrently. Message passing systems. In the above section, we showed how cooperating processes can communicate in a shared memory environment. The scheme requires that these processes share a region of memory and that the code for accessing and manipulating the shared memory be written explicitly by the application programmer. Another way to achieve the same effect is for the operating system to provide the means for cooperating processes to communicate with each other via a message passing facility. Message passing provides a mechanism to allow processes to communicate and to synchronize their actions without sharing the same address space. It is particularly useful in a distributed environment where the communicating processes may reside on different computers connected by a network. For example, an internet chat program could be designed so that chat participants communicate with one another by exchanging messages. A message passing facility provides at least two operations: send message, receive message. Messages sent by a process can be either fixed or variable in size. If only fixed-sized messages can be sent, the system-level implementation is straightforward. This restriction, however, makes the task of programming more difficult. Conversely, variable-sized messages require a more complex system-level implementation, but the programming task becomes simpler. This is a common kind of trade-off seen throughout operating system design. If process P and Q want to communicate, they must send messages to receive messages from each other. A communication link must exist between them. This link can be implemented in a variety of ways. Here are several methods for logically implementing a link and the send function, receive function operations. Direct or indirect communication, synchronous or asynchronous communication, automatic or explicit buffering. Naming. Processes that want to communicate must have a way to refer to each other. They can use either direct or indirect communication. Under direct communication, each process that wants to communicate must explicitly name the recipient or sender of the communication. In this scheme, the send function and receive function primitives are defined as send open brackets p message close brackets send a message to process P, receive open brackets Q message close brackets receive a message from process Q. A communication link in this scheme has the following properties. A link is established automatically between every pair of processes that want to communicate. The processes need to know only each other's identity to communicate. A link is associated with exactly two processes. Between each pair of processes there exists exactly one link. This scheme exhibits symmetry in addressing, that is, both the sender process and the receiver process must name the other to communicate. A variant of the scheme employs asymmetry in addressing. Here, only the sender names the recipient. The recipient is not required to name the sender. In this scheme, the send function and receive function primitives are defined as follows. Send open brackets P message send a message to process P, receive ID message, receive a message from any process. The variable ID is set to the name of the process with which communication has taken place. The disadvantage in both of these schemes, symmetric and asymmetric, limited modularity of the resulting process definitions. Changing the identifier of a process may necessitate examining all other process definitions. All references to the old identifier must be found so that they can be modified to the new identifier. In general, any such hardcore techniques where identifiers must be explicitly stated are less desirable than techniques involving indirection. With indirect communication, the messages are sent to and received from mailboxes or ports. A mailbox can be viewed abstractly as an object into which messages can be placed by processes and from which messages can be removed. Each mailbox has a unique identification. For example, POSIX message queues use an integer value to identify a mailbox. A process can communicate with another process via a number of different mailboxes, but two processes can communicate only if they have a shared mailbox. The send function and receive function primitives are defined as follows. Send, open brackets A, message, close brackets. Send a message to mailbox A. Receive, open brackets A, message, close brackets. Receive a message from mailbox A. In this scheme, a communication link has the following properties. A link is established between a pair of processes only if both members of the pair have a shared mailbox. A link may be associated with more than two processes. Between each pair of communicating processes, a number of different links may exist, with each link corresponding to one mailbox. Now suppose that processes P1, P2 and P3 all share mailbox A. Process P1 sends a message to A, while both P2 and P3 execute a receive function from A. Which process will receive the message sent by P1? The answer depends on which of the following methods we choose. Allow a link to be associated with two processes at most. Allow at most one process at a time to execute a receive function operation. Allow the system to select arbitrarily which process will receive the message, that is, either P2 or P3, but not both, will receive the message. The system may define an algorithm for selecting which process will receive the message. For example, round robin, where processes take turns receiving messages. The The system may identify the receiver to the sender. A mailbox may be owned either by a process or by the operating system. If the mailbox is owned by a process, that is, the mailbox is part of the address space of the process, then we distinguish between the owner, which can only receive messages through this mailbox, and the user, which can only send messages to the mailbox. Since each mailbox has a unique owner, there can be no confusion about which process should receive a message sent to this mailbox. When a process that owns a mailbox terminates, the mailbox disappears. Any process that subsequently sends a message to this mailbox must be notified that the mailbox no longer exists. In contrast, a mailbox that is owned by the operating system has an existence of its own. It is independent and is not attached to any particular process. The operating system then must provide a mechanism that allows a process to do the following: create a new mailbox, send and receive messages through the mailbox, delete a mailbox. The process that creates a new mailbox is that mailbox's owner by default. Initially, the owner is the only process that can receive messages through this mailbox. However, the ownership and receiving privilege may be passed to other processes through appropriate system calls. Of course, this provision could result in multiple receivers for each mailbox. Synchronization. Communication between processes takes place through calls to send function and receive function primitives. There are different design options for implementing each primitive. Message passing may be either blocking or non-blocking, also known as synchronous and asynchronous. Blocking send. The sending process is blocked until the message is received by the receiving process or by the mailbox. Non-blocking send. The sending process sends the message and resumes operation. Blocking receive. The receiver blocks until a message is available. Non-blocking receive. The receiver retrieves either a valid message or a null. Different combinations of send function and receive functions are possible. When both send function and receive functions are blocking, we have a rendezvous between the sender and the receiver. The solution to the producer-consumer problem becomes trivial when we use blocking send function and receive function statements. The producer merely invokes the blocking send function call and waits until the message is delivered to either the receiver or the mailbox. Likewise, when the consumer invokes receive function, it blocks until a message is available. The producer process using message passing. The consumer process using message passing. Buffering. Whether communication is direct or indirect, messages exchanged by communicating processes reside in a temporary queue. Basically, such queues can be implemented in three ways. Zero capacity. The queue has a maximum length of 0, thus, the link cannot have any messages waiting in it. In this case, the sender must block until the recipient receives the message. Bounded capacity. The queue has infinite length n, thus, at most n messages can reside in it. If the queue is not full when a new message is sent, the message is placed in the queue, either the message is copied or a pointer to the message is kept, and the sender can continue execution without waiting. The link's capacity is finite, however. If the link is full, the sender must block until the space is available in the queue. Unbounded capacity. The queue's length is potentially infinite, thus, any number of messages can wait in it. The sender never blocks. The zero capacity case is sometimes referred to as a message system with no buffering. The other cases are referred to as systems with automatic buffering. Methods for handling deadlocks. Generally speaking, we can deal with the deadlock problem in one of three ways. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlocked state. We can allow the system to enter a deadlocked state, detect it, and recover. We can ignore the problem altogether and pretend that deadlocks never occur in the system. It is then up to the application developer to write programs that handle deadlocks. 3 methods of handling deadlocks. To ensure that deadlocks never occur, the system can use either a deadlock prevention or a deadlock avoidance scheme. Deadlock prevention provides a set of methods to ensure that at least one of the necessary conditions cannot hold. These methods prevent deadlocks by constraining how requests for resources can be made. Deadlock avoidance requires that the operating system be given additional information in advance concerning which resources a process will request and use during its lifetime. With this additional knowledge, the operating system can decide for each request whether or not the process should wait. To decide whether the current request can be satisfied or must be delayed, the system must consider the resources currently available, the resources currently allocated to each process, and the future requests and releases of each process. If a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may arise. In this environment, the system can provide an algorithm that examines the state of the system to determine whether a deadlock has occurred and an algorithm to recover from the deadlock, if a deadlock has indeed occurred. In the absence of algorithms to detect and recover from deadlocks, we may arrive at a situation in which the system is in a deadlocked state yet has no way of recognizing what has happened. In this case, the undetected deadlock will cause the system's performance to deteriorate because resources are being held by processes that cannot run and because more and more processes, as they make requests for resources, will enter a deadlocked state. Eventually, the system will stop functioning and will need to be restarted manually. Although this method may not seem to be a viable approach to the deadlock problem, it is nevertheless used in most operating systems. Expense is one important consideration. Ignoring the possibility of deadlocks is cheaper than the other approaches. Since in many systems deadlocks occur infrequently, say once per year, the extra expense of the other methods may not seem worthwhile. In addition, methods used to recover from other conditions may be put to use to recover from deadlock. In some circumstances, a system is in a frozen state but not in a deadlocked state. We see the situation, for example, with a real-time process running at the highest priority or any process running on a non-preemptive scheduler and never returning control to the operating system. The system must have manual recovery methods for such conditions and may simply use those techniques for deadlock recovery. Monitors. We present a solution to the dining philosopher's problem that ensures freedom from deadlocks. Although semaphores provide a convenient and effective mechanism for process synchronization, using them incorrectly can result in timing errors that are difficult to detect, since these errors happen only if particular execution sequences take place, and these sequences do not always occur. We have seen an example of such errors in the use of counters in our solution to the producer-consumer problem. To illustrate how, we review the semaphore solution to the critical section problem. All processes share a semaphore variable mutex, which is initialized to 1. Each process must execute wait mutex function before entering the critical section and signal mutex function afterward. If this sequence is not observed, 2 processes may be in their critical sections simultaneously. Next, we examine the various difficulties that may result. Note that these difficulties will arise even if a single process is not well behaved. This situation may be caused by an honest programming error or an uncooperative programmer. Suppose that a process interchanges the order in which the wait function and signal function operations on the semaphore mutex are executed, resulting in the following execution. In this situation, Several processes may be executing in their critical sections simultaneously, violating the mutual exclusion requirement. This error may be discovered only if several processes are simultaneously active in their critical sections. Note that the situation may not always be reproducible. Suppose that a process replaces signal mutex with a wait mutex. That is, it executes wait mutex, so on, critical section, so on, wait mutex. In this case, a deadlock will occur. Suppose that a process omits the wait mutex or the signal mutex functions, or both. In this case, either mutual exclusion is violated or a deadlock will occur. These examples illustrate that various types of errors can be generated easily when programmers use semaphores incorrectly to solve the critical section problem. To deal with such errors, researchers have developed high-level language constructs. In this section, we describe one fundamental high-level synchronization construct, the monitor type. Monitors include the following: monitor usage, dining Philosophers solution using monitors, implementing a monitor using semaphores, resuming process within a monitor. Monitor usage. An abstract data type, or ADT, encapsulates data with a set of functions to operate on that data that are independent of any specific implementation of the ADT. A monitor type is an ADT that includes a set of programmer-defined operations that are provided with mutual exclusion within the monitor. The monitor type also declares the variables whose values define the state of an instance of that type, along with the bodies of functions that operate on those variables. The syntax of a monitor type is shown in figure below. The representation of a monitor type cannot be used directly by the various processes. Thus, a function defined within a monitor can access only those variables declared locally within the monitor and its formal parameters. Similarly, the local variables of a monitor can be accessed by only the local functions. The monitor construct ensures that only one process at a time is active within the monitor. Consequently, the programmer does not need to code this synchronization constraint explicitly. Figure below, schematic view of a monitor. However, the monitor construct as defined so far is not sufficiently powerful for modeling some synchronization schemes. For this purpose, we need to define additional synchronization mechanisms. These mechanisms are provided by the condition construct. A programmer who needs to write a tailor-made synchronization scheme can define one or more variables of type condition. Condition X, Y. The only operations that can be invoked on a condition variable are wait function and signal function. The operation x.wait function means that the process invoking this operation is suspended until another process invokes x.signal function. The x.signal function operation resumes exactly one suspended process. If no process is suspended, then the signal function operation has no effect. That is, the state of x is the same as if the operation had never been executed. See figure below, monitor with condition variables. Contrast this operation with the signal function operation associated with semaphores, which always affects the state of the semaphore. Now suppose that when the x.signal function operation is invoked by a process P, there exists a suspended process Q associated with the condition X. Clearly, if the suspended process Q is allowed to resume its execution, the signaling process P must wait. Otherwise, both P and Q would be active simultaneously within the monitor. Note, however, that conceptually both processes can continue with their execution. Two possibilities exist. 1. Signal and wait. P either waits until Q leaves the monitor or waits for another condition. 2. Signal and continue. Q either waits until P leaves the monitor or waits for another condition. There are reasonable arguments in favor of adopting either option. On the one hand, since P was already executing in the monitor, the signal and continue method seems more reasonable. On the other hand, if we allow thread P to continue, then by the time Q is resumed, the logical condition for which Q was waiting may no longer hold. A compromise between these two choices was adopted in the language concurrent Pascal. When thread P executes the signal operation, it immediately leaves the monitor. Hence, Q is immediately resumed. Many programming languages have incorporated the idea of the monitor as described in this section, including Java and C#. Other languages such as Erlang provides some type of concurrency support using a similar mechanism. Dining Philosophers' solution using monitors. Next, we illustrate monitor concepts by presenting a deadlock-free solution to the Dining Philosopher's problem. This solution imposes the restriction that a philosopher may pick up her chopsticks only if both of them are available. To code this solution, we need to distinguish among three states in which we may find a philosopher. For this purpose, we introduce the following data structure. Philosopher I can set the variable state I equals eating only if her two neighbors are not eating. We also need to declare condition self 5. This allows philosopher I to delay herself when she is hungry but is unable to obtain the chopsticks she needs. We are now in a position to describe our solution to the dining philosopher's problem. The distribution of the chopsticks is controlled by the monitor dining philosophers, whose definition is shown in program below. A monitor solution to the dining philosopher problem. Each philosopher, before starting to eat, must invoke the operation pickup function. This act may result in the suspension of the philosopher process. After the successful completion of the operation, the philosopher may eat. Following this, the philosopher invokes the put-down function operation. Thus, philosopher 5 must invoke the operation pickup function and put-down function in the following sequence. It is easy to show that this solution ensures that no two neighbors are eating simultaneously and that no deadlocks will occur. We note, however, that it is possible for a philosopher to starve to death. We do not present a solution to this problem but rather leave it as an exercise for you. Implementing a monitor using semaphores. For each monitor, a semaphore mutex initialized to 1 is provided. A process must execute wait mutex function before entering the monitor and must execute signal mutex function after leaving the monitor. Since a signaling process must wait until the resumed process either leaves or waits, an additional semaphore, next, is introduced initialized to 0. The signaling processes can use next to suspend themselves. An integer variable next count is also provided to count the number of processes suspended on next. Thus, each external function f is replaced by as follows. Mutual exclusion within a monitor is ensured. We can now describe how condition variables are implemented as well. For each condition x, we introduce a semaphore xSem and an integer variable xCount, both initialized to 0. The operation x.wait function can now be implemented as follows. The operation x.signal function can be implemented as follows. This implementation is applicable to the definitions of monitors given by both Hoare and Brinch-Hansen. Resuming processes within a monitor. We turn now to the subject of process resumption order within a monitor. If several processes are suspended on condition x and an x.signal function operation is executed by some process, then how do we determine which of the suspended processes should be resumed next? One simple solution is to use a first-come, first-served FCFS ordering so that the process that has been waiting the longest is resumed first. In many circumstances, however, such a simple scheduling scheme is not adequate. For this purpose, the conditional wait construct can be used. This construct has the form x.waitC function, where C is an integer expression that is evaluated when the wait function operation is executed. The value of C, which is called a priority number, is then stored with the name of the process that is suspended. When x.signal function is executed, the process with the smallest priority number is resumed next. To illustrate this new mechanism, consider the resource allocator monitor shown in program below, which controls the allocation of a single resource among competing processes. A monitor to allocate a single resource. Each process, when requesting an allocation of this resource, specifies the maximum time it plans to use the resource. The monitor allocates a resource to the process that has the shortest time allocation request. A process that needs to access the resource in question must observe the following sequence, where R is an instance of the type resource allocator. Unfortunately, the monitor concept cannot guarantee that the preceding access sequence will be observed. In particular, the following problems can occur. A process might access a resource without first gaining access permission to the resource. A process might never release a resource once it has been granted access to the resource. A process might attempt to release a resource that is never requested. A process might request the same resource twice without first releasing the resource. The same difficulties are encouraged with the use of semaphores, and these difficulties are similar in nature to those that encouraged us to develop the monitor constructs in the first place. Previously, we had to worry about the correct use of semaphores. Now we have to worry about the correct use of higher-level programmer-defined operations with which the compiler can no longer assist us. One possible solution to the current problem is to include the resource access operations within the resource allocator monitor. However, using this solution will mean that scheduling is done according to the built-in monitor scheduling algorithm rather than the one we have coded. To ensure that the processes observe the appropriate sequences, we must inspect all the programs that make use of the resource allocator monitor and its managed resource. We must check two conditions to establish the correctness of the system. First, user processes must always make their calls on the monitor in a correct sequence. Second, we must be sure that an uncooperative process does not simply ignore the mutual exclusion gateway provided by the monitor and try to access the shared resource directly without using the access protocols. Only if these two conditions can be ensured can we guarantee that no time-dependent errors will occur and that the scheduling algorithm will not be defeated. Although this inspection may be possible for a small, static system, it is not reasonable for a large system or a dynamic system.